to discuss a topic that makes use of some similar mechanisms in any logic, but is different. It has textured features of its own. And that is the issue, ladies and gentlemen, of calibration, model calibration. I'm going to go through this quickly and try to emphasize some of the practical things that will help you with your problem set. Your problem set indeed focuses on this issue. It may go into some of next time, but I'm going to see what I can hit in the next 20 minutes, 25 minutes. Okay, so model calibration is a phase, like model sensitivity analysis, that occurs partway through the modeling process. Often we're trying to arrive at estimates for model parameters that are hard to find through other sources. Okay, so sometimes we have model parameters we don't have good data on. All we have are best guesses. But often we'll have data that are not about any one parameter in isolation. They're not estimates of that parameter value, but there's something about model behavior as a whole, or the behavior of pieces of the model, system behavior as a whole, observed system behavior from the world. Maybe we know something about the wait times in a hospital. That doesn't tell us about exactly how fast people are getting treated, or how long it takes a doctor to report to the, to go to the patient in the procedure room, or exactly how long it takes to file some paperwork after the visit, or what have you. But it's something that results from any of those things. We may have data on the number of people who have been sick over the course of an outbreak, but that's not data about the likelihood of transmission given a contact between a susceptible and infected. It's not data about the contact rate. It's not data specifically about the recovery rate. It's a combination of, it results from all of them. All of them impact it, but it's not itself about those things. It doesn't allow us to directly go to an estimate of those quantities, of those parameters. But surely it tells us something about them. The fact that we have a curve of this sort or that sort, it implies something about them. It constrains what possible values they could be in some cases. The fact that we have an outbreak at all occurring may be indicative, for example, that that the transmission, the contact rate, transmission rate, etc., combined guarantee that a given infected infects more than one person. It constrains what those values could be. Maybe not at an individual level, but collectively. It constrains possible interpretation. So often, ladies and gentlemen, we have data on emergent behavior of a system. It relates not to a particular parameter in isolation, but to possible combinations of possible parameter values. Okay? Some parameters may not even be observable. It's hard to get empirical data on them. We don't have a test to test that thing or what have you. But our model involves that. We're hypothesizing about that. But we might have data of other observables that relate to this. Maybe the data that we have doesn't have the detailed breakdown. It doesn't have the data broken down by age group or whatever that we're seeking. And so it doesn't allow us to go to one parameter value, but instead, but it tells us something. There's some information there about possible values. Okay, and often we seek to leverage this data in modeling. We seek to leverage it to estimate parameter values, and there are several ways we can do it. Some of them are purely algebraic. So we're going to seek a model that matches all of this data. This is data from improved people related to different cases of diabetes and diabetic end-stage renal disease over time in Saskatchewan. We're seeking a model that simultaneously matches all these time series. It's quite different from what you're seeking in a regression model, for example. You're matching one particular set of data that you're using to regress your statistical model against. Here, we're getting our simulation model to match all of these. We expect it as a matter of face validity, as a matter of basic plausibility to match each and every one of these time series. Does that make sense? We're holding it up to a high standard. We have this model that has many moving parts, and we're saying if this model is predictive, if this model is valid, if this model has substance, if it's accurately characterizing the situation, we should be able to explain a lot of different things. We should be able to match it against a lot of data. And in fact, and this is a key point, it's a testable notion, it's a testable phrase, we might do cross-validation. We say, okay, we'll build this data with respect to data, put in data from these sources. And then we'll see if we can predict the data from these other sources. We won't actually tell it about it. We won't put it into the model. We won't presuppose it. Instead, we see if it predicts it. In any case, we want the model to predict a bunch of things. And sometimes we can take some data and we can manually back it out. We do this all the time, engineering and in physics and so on. We have some data, and it's not data about any one parameter, but it implies something very straightforward about parameters. And it involves some algebra and often imposing some pretty strong assumptions. Okay? So we might assume a stock is in equilibrium, for example. So if we have the outflow, we'll assume the inflow is basically equal to the outflow. Or we might assume that the outflow we know the rate of outflow, and we know the rough time associated with the outflow, and we can calculate what's the value of the stock, assuming it's a first order delay. So we know X over D is the outflow, and we know what D is, and D is the mean time to flow out of that stock, so we can calculate X. Okay. So, it often involves little puzzles like this. Maybe, for example, we know we want to find out what's the prevalence of diabetes among men and women in the population. We don't know that, but we know the breakdown of the population by sex, the whole population's prevalence of diabetes, what fraction of the whole population is diabetes, in other words, and the ratio of diabetes between men and women. Maybe we have data that tells us these things we found in articles or what have you. Then we can figure out what this must be by simple algebra. We do this simple algebra quite a lot. We sort of figure things out, okay, what must it be? And often that involves some assumptions. Sometimes quite questionable assumptions, like assuming equilibrium or what have you. And sometimes it's just not possible to do this because it's too complex. So what we're going to do today, what we're going to be looking at in the calibration process, and in fact the model before you, the model we've been using for stochastics and sensitivity analysis, we're going to be using it now for calibration. And the idea here, folks, is to tune parameter values to best match the empirical data, so that the model best matches the empirical data, I should say. We tune the parameter values so that the model has the best possible match against what we know from the real world. Does that make sense? We observe data from the real world, maybe with respect to one time series, maybe with respect to many time series, and we adjust certain parameter values that we don't know so that it matches those observed data. Does that make sense? We adjust those assumptions. So, ladies and gentlemen, I stand up here and I spout before you a set of abstractions. And I'm hoping they're sinking in. But there's something to be said for concrete exposure to this. So, ladies and gentlemen, let us fire up your end logics again. And let us go to that same model, but a different experiment. Okay? Let's go here. Instead of focusing on this final experiment, in which we did different sensitivity analysis, we're going to go up to this calibration experiment, which you should see with a stride, a whirlpool, a vortex, a maelstrom here. And I would like you to run this experiment. This is an alternative type of experiment, and it's an experiment that perhaps you've never seen before. And what we'll see is a experiment window. This is the experiment running here. We haven't yet started the actual simulation. And we see before us, in yellow, a set of historic data. Okay? Right now, this is a single time series. So this graph shows over time on the x-axis. It shows on the y-axis the number of people infected. Okay? And we're going to run here this model, and we'll see the model aspiring, trying to match this data as closely as possible. And you'll see it trying to explore different values. So there's some historic data in yellow again. There's current output, where it's kind of trying different possible parameter values, and it's trying to get close to this historic data. And you'll see that each of these matches is in fact being marked. It's being graded. It's being judged by how good a fit it lies to this actual historic data. So it's kind of flipping around. You'll notice up here, it's trying different combinations of parameter values, okay? So right now it's trying 1.5, 1.3, 1.9, 1.0, and it's different combinations. And it's getting closer over time. It's getting closer to this underlying historic value. And that reflects the fact that its so-called objective function, its error function, its energy function, for those from physics background, is getting lower and lower. In other words, its distance from this historic data is getting less and less far. So it's trying different values, and it's judging them all through the period here and getting close. You notice now it's getting very close indeed, right? This is the best value that it's gotten, and when it comes down, when it finds another better value, it'll update this value here, okay? So it'll find sort of a better combination of values. So here we have a contact rate and infection probability, and it's finding combinations of these values, okay? These are all, you can see up here, the myriad of actual explorations it's performed with different combinations values, and many of them have not been on the efficient frontier. They have not been such that they yield the best matches so far. So, you know, it's gotten down to this point, and it's gone on and tried others, and they have been nearly as fruitful, and then it finds one that's even lower, and now it finds one that's even lower. And you could run this for a long period of time, for hours, for days, and it would successfully try to find better matches to this historic data. But you see, it's already, you know, fairly close there. It's doing a pretty good job of matching it, right? Yes.
So let's say that you've done this, and it comes up with something that matches your historical data fairly well.
Yeah.
But then when you actually look at those values, they completely don't make sense. They lack these possibilities.
Yeah.
Does that then put you a problem with the way you design your model?
Yeah. So, excellent question. So Sarah's question was, suppose you go through a long process of calibration, perhaps not with respect to just one time series, but several, right? As I've asked you to do for problem set 4, where you're going to be adding another time series in here and trying to match that as well at the same time. And let's suppose that you get out, it seems like a good match, but the data lack apparent phase of plausibility. They're way off from what seems meaningful. Well, I will tell you that it is failures in this calibration. Well, I say failure. That almost presupposes a normative judgment. It is difficulties encountered in this process that are some of the biggest insights for modeling, because this process is one of the key processes that keeps us honest as modelers. Okay, the discoveries you make in this process often shape in a very substantive way our learning and by extension our models. And one of the difficulties we might encounter is what Sarah just mentioned. This difficulty associated with if there's a good match but the parameter values are way off. That suggests to me, that smells to me a lot like questioning model structure, okay? That there's some assumptions you've made about model structure which may have seemed plausible, but in order to force fit the data into that model structure, it's had to make implausible assumptions given parameters, okay? And I would note, Sarah, that this same problem often comes out when because often in this calibration, you will say, well, we'll see it in just a moment here. fact, why don't we switch to that screen right now. In this calibration, you will see to define the calibration that you're actually varying parameters within certain ranges. And so, for example, you may only limit those parameters of interest to certain ranges that seem have phase plausibility, and then you can't find any solution that gives decent results. And the question is, what do you do? Then it's two sides of the same coin, because depending on whether you allow it or not, you've discovered your model cannot, with reasonable values of the parameters, allow this. So there's a couple of combinations. There's a couple of possibilities. One is that maybe there's many things that give good matches, and this is just one of them. Okay. And there's ways to check that systematically. You may restrict, for example, those parameters to smaller values. See if it also gets a very good match, but just within a tighter bounds. In which case, now you've got a difficult situation where you have multiple explanations, multiple hypotheses, or at least multiple details of those hypotheses, which would explain in a similar fashion that data. Okay, and so that might point you to trying to find more data, or trying to find at least rough qualitative checks on these data values. Another thing that you might do, though, is you might search question model structure in an important way. And here you might try disaggregating a certain thing involved. I'll give you a case where this sort of thing happens. Take a system dynamics model. Okay? System dynamics model seeking to kind of characterize an outbreak in a context of the necessary assumptions in system dynamics of random mixing, right? But imagine what's really going on is a situation where you have distance-based networks. It's not random mixing. It's actually very localized mixing. Or imagine a situation where you have a scale-free network in the background. So some people have tons of heterogeneity, have tons of number of partners, and others have very few. In these cases, you may calibrate your system dynamics model against it. If you're lucky, it may match the data. Okay. In some cases, it will just balk. It will just say, "I can't do it. Sorry," and that tells you a lot, because it says basically, "Hey, this ain't fitting together. This is not a consistent hypothesis. You need to go challenge that hypothesis at different places, often by changing model structure." If it does model it, it may only do so with very high values of contact rate that seem totally implausible. It says, most people in the population share needles and use intravenous drugs with, at least 10 times a year. And, that lacks epidemiological plausibility. So in those cases, what it suggests is we actually may need to modify that model to accommodate, for example, heterogeneity in the population. The fact that some people have lots of connections and some people have few. And in a system dynamics context, it may lead you to so-called stratify the model to create essentially copies of the model for people with different numbers of connections. Or it may lead you to actually adopt a different model structure. And there's some clever ways of building system dynamics models to try to take into account heterogeneity in terms of number of connections furthermore. But the point is that's where it pushes back at you. And that's really a good thing. It takes time. It delays the schedule. But that's where the learning occurs. It would be disconcerting if every simulation model we threw at this could be calibrated perfectly. That would be deeply disconcerting because it doesn't tell us anything about the correctness of our assumptions. This is what, as I say, this is one of the key things that keeps us honest. Let me throw it out to the class level. Let's suppose the model perfectly matches the data. So we come out with a model, reasonable values of parameters, and it matches all the data you've thrown at it. Is that model correct? Not necessarily. It has a certain phase plausibility. It's a certain plausibility as based on what's known as a hypothesis. It hasn't been disconfirmed by the data, but it has not been proven by any stretch of the imagination. It has not been proven to be correct. It has been shown to be consistent with data, which raises confidence. Really, this is an issue of confidence building. It shows it's a competitive model, at least as far as that data, but it does not show it's correct. And one of the best practices we do, which I alluded to earlier, is what's called cross-validation. And that's, again, a term I want you to know, which is where, again, we use to match the model against part of the data, to match it against 3 time series. We see if it can predict the 4th one, without in any way presupposing it, without in any way telling it about that series, without in any way putting it into there, without in any way calibrating it to it. We see if that 4th one it predicts automatically. If it does, that again raises confidence. It raises confidence that this model has some substance to it. It can surprise us, or it can generate new insights. It can generate new information that we didn't put into it. That raises confidence, because at some point you may be concerned that you're overfitting the model. You're getting it to exactly match all these things, but it lacks generality. And if you can get it to predict other things from the limited data you know, that may raise, will substantially raise. So this calibration process is a key one, and we're helping define these dynamic hypotheses for the observed data. So it helps us leverage large amounts of diffuse information. Don't help us estimate one parameter, but instead help us collectively estimate a bunch of the parameters. So let's just talk a little bit about what this is and how it operates. And I'm going to let you futz with the model. I'm going to let you observe my slides and try to learn from the model. And I'm going to let you, come next Tuesday, come back to me with questions about what's going on. Okay? You're going to work with this model a little bit, see if we can test your understanding about how it's working. Okay, so big picture. Most calibration algorithms use what's called global optimization. How many people have encountered in a class optimization? Okay, just a couple, yeah. So the idea here is we're trying to adjust parameter values such that we're trying to find combinations of those parameter values so that the model will most closely match the data we've told it about, right? This data may be in the form of time series. It may be in the form of just numbers, estimates for certain things. The fraction of population who are infected as of this time or what have you. And there's this optimization algorithm that runs the model again and again and again and again with different combinations of parameters to try to find the best match. I'm glossing over something very important. But the basic idea here is that we have many important things. Here we have a parameter space. We can imagine having 3 parameters, which just for brevity I've shown with Greek letters. And we're examining we're examining many combinations of them. We're trying to find combinations of them, searching within this cube, in the volume of this cube, to find that combination that hits the sweet spot. It matches as best as possible the different values, okay? So in order to do this, we have to provide some way of describing what's a good fit, what's a bad fit. How do we judge that it's a good fit that this model has with these particular parameter values? How do we say this fit is better than this other? We need to provide a metric, a measure of goodness, a measure of goodness or a measure of badness of the thing. Either one will do. Okay. So often we do so with a badness measure. What this is called an energy function. Objective function. We try to minimize it. We try to minimize the badness of the fit, how bad the fit is, okay? And the badness of the fit is associated with discrepancy. It's something about the distance between what the model predicts and what's actually observed, okay? So some sort of discrepancy, you know? And to make it dimensionally consistent, we don't want to measure a discrepancy in people, and then a discrepancy in dollars, and a discrepancy in deer or whatever, and sum them together. It doesn't make sense semantically. So we actually turn it typically into a dimensionless quantity, a fractional value, for example, and we sum them up. Okay. So we're 10% off in people and 5% off in our prediction of the number of cars and 1% off in our prediction of cost or something like that. We sum them up. Okay, so we don't really have time to go into this right now, but it bears noting that choosing a discrepancy metric, choosing how we quantify, how we measure, how we specify our discrepancy, this metric we use, that you want a couple properties for it. You want it to be dimensionless. We want to be able to add these discrepancies together, regardless of whether they're about people or cost or what have you. It should be weighted. We might want to weight some more because we're more confident about the data. It'd be kind of nice from a mathematical perspective to be able to differentiate it. It's not key for certain types of things, but it can be favorable in certain cases to prove a minimum or what have you. And it should be concave. Two small discrepancies spread across two different variables, two different parameters are generally considered more desirable compared to one large discrepancy. If that sum concentrated on one parameter. It should be symmetric. Being off by a factor of 2 should have the same effect on the upper side and then the lower side. It should be non-negative. We don't want one discrepancy to be considered negative. Oh, I did a great job with this, and so it cancels out another discrepancy in another thing. It should go from 0 and up, and it should be finite. It shouldn't yield an infinite value. So this is one example discrepancy metric. We take a difference between the historic data, or the data we know empirically, the data that's observed, subtract off from it the model, and we divide it by the average of the two. This works for values with historic and model are greater than or equal to 0. Well, greater than 0, and there's an easy accommodation for equal to 0. And then we square it. We square it. That helps us kind of favor two small ones compared to one big one. One big one of size, so two small ones of size 1 each, sum up, 1 plus 1 equals 2. One big one of size 2, square it, size 4. It's bigger than the 2. So 1 squared plus 1 squared equals 2. We prefer that because it's lower than, it's smaller. We're trying to minimize this discrepancy to something that's 2 squared, which is 4. Okay. Does that make sense? Okay. And we often will pick weighting to say, well, we care more about these certain things. We really want this. It depends on model purpose. What are we trying to do with this model? Are we trying to use it to predict human health or ecosystem health or what have you? And so we may weight it according to that, how much uncertainty there is in the historic data, whether the data exists. Okay. So an optimization algorithm is used for this. And it can be very simple. For example, it can start at random. This is a very simple one. This is the most trivial one, like Benson uses. It starts at a random position, and then it kind of jiggles around. You try to jiggle around the different parameters, try different modifications of parameters, and it keeps on choosing those that improve it. Okay, so improve it goes there. And goes in a direction to try to improve this thing. And at some point, it's going down, and maybe it starts getting stuck, and it can't get any better. It's searching around, and then boom, it goes down again, and searches around, and going down, and boom, down to the ground there. It goes down there, and it stays down there, and it can't get any better. And at some point, it gives up and says, "I think I've got the best one." So, we have this sort of random position start, random movement, preferentially accepting things that bring us down, bring us lower the discrepancy observed, and then at some point we minimize it. Noise is often very important to this. We don't want to just do a totally deterministic algorithm where it goes to the minimum place and stays there. Why not, ladies and gentlemen? What would happen here if I lowered it to the minimum and I didn't have any noise added, so I'm not jiggling around? What would happen? Go to a local minimum right here in the chalkboard, just below the chalkboard here in the chalk tray, and it won't go any lower. it needs some noise to sort of knock it around, to get it out of these local minima, to get it over to this lip here where it can go down further. So Benson actually uses a deterministic algorithm. So it's just going down in the direction of the gradient, I think. So it's just trying to figure it out, oh, based on the math of the model, it's going to minimize it. Or it actually, I think it just goes deterministically and it goes down. Then any logic actually has noise, so it's adding things, and so eventually we'll get out of the local minima and continue down. And there's clever ways of doing it. Simulated annealing, where you're adding more noise early on and then make it successively less noise, etc. Okay. So this algorithm we saw earlier, it was varying these parameters within these ranges, and it was adjusting them, and it was selecting values that were particularly favorable, and it was using those values to start new runs. It was using what's called a genetic algorithm. It was combining the best values it got so far to get yet new values, for example. I don't know all the details of the algorithm. You can read about it through the OptQuest optimization algorithm, and it tries to find the best possible. Next time, we're out of time now, but next time we will try to examine how those discrepancies are calculated and to read about some of these issues. And, for example, I'm pretty sure it uses a genetic algorithm and combines best values. You can read in the OptQuest engine, but we'll see about mechanically how it interfaces with the model, because this will be important for your problem set 4, because you're going to be modifying this mechanism in order to implement your extension of this model to take into account multiple matches at the same time. Okay? So that's all for today. We've seen sensitivity analysis and associated tools, Latin hypercubes, orthogonal arrays, Monte Carlo sampling with parameters. Talked about reducing the number of parameters, combinatorial explosion, and we talked about calibration, some of the challenges associated with estimating model parameters, some of the philosophy in terms of things you got to be cautious about. Next time, we'll probably see a little bit of this, and then we'll go on to a different topic. Okay? So that's all for today. Yeah. Yes. Good evening. Yeah. Okay. So let me just stop this here.